In the presence of multicollinearity, fitting a linear model to a data set becomes extremely difficult. The reason for difficulty is when we say multicollinearity is present in the data, what we mean is the predictor variables used in the linear model are correlated to each other. When we have two predictors which are correlated to one another, then the effect of one cannot be distinguished from the other predictor. In that case, interpretation of the corresponding correlation coefficient becomes very difficult. So, in order to get rid of multicollinearity from a data set, statisticians have developed several different methods, a few of which we have discussed in a previous module titled Multicollinearity Remedies I. As a continuation of that model, this module named Multicollinearity Remedies Part 2, we will discuss some more statistical techniques to get rid of multicollinearity. In the previous module titled Multicollinearity Remedies I, we had discussed several methods to remedy multicollinearity. We had also looked at one of the more important methods, which is the principal component regression. This method is widely used by statisticians to remove multicollinearity from a data set. In the current module, it can be considered as a continuation of the first. In this module again, we will discuss some more methods of removing multicollinearity from a data set. The two methods to remedy multicollinearity that we will discuss in this module are combining cross-sectional and time series data and using the ridge regression technique. So, let us begin by discussing the combining cross-sectional and time series data technique of removing multicollinearity from a data set. So, let us begin by discussing the combining cross-sectional and time series data technique of removing multicollinearity from a data set. This method of removing multicollinearity is a variant of the a priori information method. The a priori information method is another method of detecting multicollinearity where we use prior information to estimate some of the parameters of the collinear predictor variables in a model and then plugging them into the model so that the other parameter can be estimated with more precision. So, combining cross-sectional and time series data can be considered as a variant of this method. Now, suppose we wish to study the automobile demand in the US. To that end, we assume time series data on a number of cars sold, the price of the car and consumer income. Then the model can be assumed to take the following form. Log of yt equals beta naught plus beta 1 log of pt plus beta 2 log of it plus ut, where the log that we have taken here is of natural base. Here yt is our response, which is the number of cars sold. Pt is the first predictor variable, which is average price of car, and it is the income variable and t is the time. In case of time series data, it is quite common for Pt, which is price, and It, which is income, to be correlated. If we think about it intuitively, as income of a person goes up, then the price of the commodities that he can afford also goes up. So, we can intuitively see a positive correlation between the two variables. But the model, the time series model that we had looked at in the previous slide, gives us a model which contains both these predictors as predictor variables for the response variable number of cars sold. Hence, these two variables in the model might lead to the problem of multicollinearity. So, statistician Tobin suggested a solution to the problem. He suggested that if we have cross-sectional data in addition to the time series data that we have, then we can obtain an estimate parameter beta 3 and then use this estimate to estimate the other parameters in the model with precision. Now, using cross-sectional data, we can obtain a fairly reliable estimate of beta 3, because in such data we only consider one point in time and collect data on price and income from different cross section. Thus, we assume that the prices do not vary much with time. Using this estimate, we can write the time series regression model that we have seen earlier again in the new form yt star equals beta naught plus beta 1 ln pt plus ut, where the response variable is now yt star given by ln y minus beta 3 hat ln it. That is, y star t is the value of y after removal of the income effect. Now, although this method sounds very appealing, there is a problem of interpreting the regression coefficients after we have pooled the cross-sectional data with time series data. When we had a time series model and we were trying to fit this model to a time series data, we were looking at the increase or decrease in the number of cars sold over time, and we also had data on the price of cars and also the income of individuals and how they have changed over time. However, when we pool cross-sectional data along with this time series data, in that case we are fixing time at one point and we are obtaining data cross-sectionally. Thus, when we use cross-sectional data to estimate beta 3, then beta 3 is no longer interpreted the same way as we were interpreting the time series data. That is, beta 3 did not reflect the amount of change in response over time due to the change in our predictor variables, because now we were fixing the time point and we were taking data from cross section. However, when we fit a regression model, the regression coefficients in a time series data gives us the amount of change over time for the response variable. So, due to the confusion of interpretation of the two data set, the cross-sectional and the time series data, we avoid using this method as much as possible. However, the technique has been used in many applications and can be considered when there is less variation among cross-sectional data. Now, let us move on to the more important method of removing multicollinearity in this module, which is the ridge regression technique. Ridge regression technique has been very popular with statisticians for the past, and we also use it even to this day. When we apply the method of least square to obtain the estimates of regression parameters for a data set with multicollinearity, then very poor estimates of the regression coefficients are obtained. Although these estimates, as I have mentioned several times before, these estimates are unbiased, but now they are not efficient anymore. These estimates, although unbiased, are no longer the best linear unbiased estimators of the regression parameters. By best linear unbiased estimator, we mean that these estimates are no longer the ones that have minimum variance among the class of unbiased estimators for the regression coefficient. Now, this is partly due to the fact that the least square technique requires that beta hat is the unbiased estimate of beta, and the Gauss-Markov theorem assures that the least square estimate has the lowest variance in the class of unbiased estimator. Thus, in the presence of multicollinearity, using the ordinary least square method to obtain the estimate for the regression coefficient is not feasible. Now, one method to tackle the above problem is to drop the condition that the estimator of beta is unbiased. We assume that we can find an estimator of the regression coefficient using ridge regression which might be biased but would give us a smaller variance. So, to that end, we suggest the ridge regression technique to alleviate the problem of minimum bias. Now, suppose that a biased estimator of beta is found to be beta hat star and that has a smaller variance than the unbiased estimator beta hat. Then we can define the form of the biased estimate that can be used to estimate beta hat star with minimum variance. The mean square error of beta hat star, which is the biased estimate of beta, is defined as expectation of beta hat star minus beta whole square, which can be written as variance of beta hat star plus expectation of beta hat star minus beta whole square, or MSE of beta hat star can be written as variance of beta hat star and the expression expected value of beta hat star minus beta, the difference is called bias. So we can write MSE of beta hat star equals variance of beta hat star plus the bias in beta hat star whole square. By letting the bias in beta hat star be very small, the variance of beta hat star can be made so small such that the MSE of beta hat star is less than the variance of the unbiased estimator of beta. So one of the symptoms of multicollinearity is that the effect estimates of parameters will be large. So if beta hat gives me the ordinary least square estimate of the parameter beta under the presence of multicollinearity, then the sum of square of these estimates will be a very high value. So the sum of beta hat I square, which can be written as beta 1 hat square plus beta 2 hat square plus beta p hat square, this again can be written in terms of vector beta hat as beta hat prime times beta hat, and this value will be very high if they are obtained using the ordinary least square method in the presence of multicollinearity. So we could then treat the collinearity problem by trying to minimize the error square subject to beta hat prime times beta hat less than equal to m, where we fix m for an optimum value. So we will use the Lagrangian technique of obtaining an optimum solution after imposing the constraints. So let us look at the form, the Lagrangian equation for finding the least square estimation of the regression coefficient. L equals y minus x tilde beta prime times y minus x beta tilde plus lambda times m minus beta hat beta tilde prime times beta tilde, which can be written in the summation form as follows, equals summation t equals 1 to n yt minus summation I equals 1 to p beta I tilde times xti whole square plus lambda times m minus summation I equals 1 to p beta tilde I square, where p is the number of parameters in the model or the number of predictors that we include in the model. So just like in the method of least square, we take the first order derivative of the above equation and equating it to 0, we obtain the estimates of the parameters. So the first order derivative with respect to the parameter beta j is given by delta L divided by delta b beta j equals negative 2 times sum of yt minus summation I beta I tilde times xti times xtj plus 2 times lambda beta I tilde square, and we equate it to 0. So we have summation t yt times xtj equals summation t summation I xti xtj beta I tilde plus lambda times beta tilde j, and the summation can be separated and written as summation t yt times xtj now equals summation I beta I tilde times summation t lambda times beta j tilde for all j equals 1, 2 to p. Now the complete set of all the derivatives, the first order derivatives of the Lagrangian equation with respect to the regression coefficient will give us a set of normal equations that we normally use to find the estimates. Now if we put the normal equations in matrix form, they will take the form x prime y equals x prime x plus lambda times in whole times tilde beta, where x is the matrix of predictors, beta tilde is the vector of parameters, and in is the identity matrix of order n, and lambda is called the Lagrangian multiplier. So solving the above set of normal equations, the estimates of the parameters is obtained as beta tilde equals x prime x plus lambda times in whole inverse x prime y. This is called the ridge regression estimate of the parameters. Now you can see that in case of ordinary least square, This function takes the form beta hat equals x prime x whole inverse x prime y. And in case of ridge regression, since we had imposed a restriction and used the Lagrangian equation using the Lagrangian multiplier lambda, we have an additional term of lambda times in. Now, let us take a look at the expectation of the estimate. In case of takes the form beta tilde equals x prime x plus lambda in whole inverse x prime y, which can be written as x prime x plus lambda times in whole inverse x prime. Now, replacing y with x times beta plus u, which was the original form of our regression model. So, beta tilde can now be written as x prime x plus lambda in whole inverse x prime x beta plus x prime x plus lambda in whole inverse u. Then we have taking expectation on both sides. Expectation of beta tilde equals x prime x plus lambda in whole inverse times x prime x beta, because we know the error term u is normally distributed with expectation 0. So, this expression of expectation beta tilde can be written as p times beta, where p is x times x prime x plus lambda times in whole inverse x prime x. So, the ridge regression is clearly biased. However, with the increase in lambda, the bias tends to be 0, because we can see that the first part of the expression x prime x plus lambda times in is taken in the inverse form. From the ridge regression estimate of the regression coefficients, we can find that the covariance of beta tilde will be given by sigma square times x prime x plus lambda in whole inverse x prime x times x prime x plus lambda in whole inverse. A few steps of algebra, of matrix algebra, will help the reader to arrive at this expression. I have not derived it here, but I leave it as an exercise for the student. Now, the covariance of beta tilde can be written in the form sigma square q, where q equals x prime x plus lambda in inverse x prime x times x prime x plus lambda in whole inverse. Now, we can see that covariance of beta tilde equals sigma square q is less than x prime x whole inverse. Hence, we have a biased estimator. We had seen on the previous slide when we obtained the estimate expectation of beta, that beta tilde is no longer a biased estimator. So, we have a biased estimator of beta which has a lower variance than the variance based on the estimator. Now, in case of regression, ridge regression, the most pertinent question is what would be the choice of the Lagrangian multiplier lambda. Now, we may choose a lambda that compromised bias but reduced variance, and this can be achieved by using the mean square error. The underlying idea, although, is to find a biased estimate with less variance, but we still need to find threshold of the cutoff value for lambda. This can be obtained using the MSE expression for beta tilde. MSE of beta tilde equals sigma square q plus p minus ip beta times beta prime p minus ip. We may choose to minimize the determinant or trace of the above function and find the lambda that minimizes the above expression. However, it is helpful to get the ridge trace, which is the plot of the estimates, the estimated standard error and the estimated square root of mean square error as a function of lambda. As we increase lambda, the ridge estimates of the parameters will dramatically change, but it will stabilize after a point of time, and our goal is to select a lambda that is reasonably small and still stabilizes the ridge estimates beta hat tilde. In this module, we have mostly learned about the very important technique of removing multicollinearity from a data set, namely the ridge regression technique. This is a technique where we have seen that we compromise the biasness of the estimates of our parameters, and in turn we get a biased estimate of the parameter which has a smaller variance. The main consequence of multicollinearity was that although the estimates of the parameters were still unbiased, they had a very large standard error, which made the inferential procedures faulty. So, using the ridge regression technique, we can come up with parameter estimates under a linear model setup where the estimates are biased, however, they have variances which are lower than the unbiased estimates variances.